So friends, till now we have completed the SCR and the diode, right? Now we are going to discuss some numericals based on the SCR and the diode. Check the question number 24. Question number 24 from the given sheet, right? Question number 24 from the given sheet. Actually, it is a theoretical question and it is very straightforward. Okay, so please check. Which of the following does not cause permanent damage of an SCR? Which of the following does not cause permanent damage of an SCR? Right? This question they have asked in the IES 2014 exam, as well as the same question they have asked in the GATE 96 exam, right? GATE 96 and IES 2014. Okay, so please check, understand the question. Which of the following does not cause permanent damage to the SCR? And the options are high current, high rate of rise of current, high temperature rise, and high rate of rise of voltage. Yes, which of the following does not cause, actually they have given. Okay, so what will happen? Check the option 1. If the high current will flow through the SCR, so whether it will cause the permanent damage to the SCR? Definitely. Due to the high current, what will happen? Yes, due to the high current, high heat will be generated, right? And due to that, high power loss will take due to the high current, high power loss will be taking place, and due to that, high heat will be generated, right? And this will cause the permanent damage to the SCR. Okay, so option 1 is not the correct answer. They have asked which of the following does not cause, right? Are you getting the point? Next, so option 1 is wrong. Second, high rate of rise of current, right? So if di by dt is high, what will happen? Due to the high di by dt, check the protection of SCR, right? In the high di by dt, due to the high di by dt, yes, it will cause the creation of local hotspots, and due to the creation of local hotspots, yes, it will this will damage permanently to the SCR, right? Creation of local hotspots will cause the permanent damage to the SCR. Okay, so option B is also not correct. Third, high temperature rise. High temperature rise. Yes, due to the high temperature rise, what will happen? If the temperature increases to a high value, yes, whether it will cause the permanent damage to the SCR? Definitely, it will cause the permanent damage to the SCR. Are you getting the point? Because due to the high temperature rise, yes, the high heat will be generated. Okay, and the last one, high rate of rise of voltage. Okay, so if the dV by dt is high, yes, what will happen? Due to the high dV by dt, yes, the device may cause the false triggering. Are you getting the point? False triggering. Okay, so whether dV by dt, high dV by dt will cause the permanent damage to the SCR? No. Okay, so the answer is option D. Answer is option D. Are you getting the point? Okay, so first three, A, B and C will cause the permanent damage, but the fourth one, high dV by dt, will not cause the permanent damage to the SCR. High dV by dt will cause the false triggering of the SCR, right? So false triggering, it will not lead to the permanent damage to the SCR. Are you getting the point? Okay, so the answer is answer D, right? Correct answer is option D. Option D is the correct answer. Are you getting the point? Okay, next, let us discuss next question. Check the question number 25. Check the question number 25. Okay. A power electronic switch is realized by SCR and diode. Power electronic switch is realized by SCR and diode as shown below. Right? Identify the static operating points on VI plane. Identify the static operating points on VI plane. Okay, so they have given the circuit. Here we have the SCR and here it is a diode. Okay, consider this full as a single switch. Consider this full as a single switch. Okay, and they are given the options. Option A, voltage, and here it is current, and they are saying that it is a unidirectional and bipolar in the option A, right? Option B, voltage, current, right? They are saying that bidirectional and unipolar. Option C, yes, it is given that bidirectional and bipolar, right? And option D, invalid switch combination. Invalid switch combination. Invalid switch combination, right? Invalid switch combination. Okay, now so here, yes, they have given the anti-parallel connection of SCR and diode, right? Anti-parallel connection of SCR and diode. SCR and diodes are connected in anti-parallel. Okay, and they have asked the VI operating points, static operating points on the VI plane for this full switch. Consider this full as a single diode. Consider this full as a single diode. Okay, so now here, yes, in the answer, can we redraw the network? Same switch. Yes, we are having one SCR and one diode connected in anti-parallel. Connected in anti-parallel. So, means here this plus and this minus, it indicates the polarity of the voltage. Okay, if the voltage is higher here and lower here, right, then the meaning is the voltage across the switch combination, right, is positive, right, and if it is reversed, then it is a negative. Okay, and this is the current flowing through the switch I. Okay, so this indicates the current flowing through the switch, that is the I, positive current, and reverse will be the negative current. Okay, and this indicates plus minus. Okay, plus here and minus here, it indicates the forward voltage. Okay, so are you getting the point? Yes, this is the forward voltage and this is the forward current direction. Okay, so please check. Let us first discuss for the directional, that is the unidirection or the bidirection. Okay, so in the unidirection or bidirection, generally on which state we concentrate? For unidirection and bidirection, we concentrate generally on conduction state, right? We generally concentrate on conduction state, right? So suppose if these two are in the conduction mode, right? So if this is in the conduction mode, the thyristor will allow the current in this direction, that is the forward current is allowed by this switch. Yes, right? Similarly, suppose if the diode is in the on state, so whether the current will flow in the opposite direction also, right? Yes, right? So when thyristor is in the on state, the current allowed, that is current will flow from this point to this point, right, in this direction through the thyristor. Okay, means the current will be flowing in the positive direction. Okay, next similarly, when diode is in the on state, current will flow from this terminal to this terminal, means current will flow in the opposite direction. Okay, means this switch combination allows the forward current as well as reverse current, positive current as well as negative current. So it is a bidirectional switch. Are you getting the point? So it is a bidirectional switch. So switch is bidirectional. This switch is a bidirectional. Switch is bidirectional, right? Switch is bidirectional. Okay. Next, let us check the polarity. That is a unipolar or bipolar. Okay. So suppose if as diode is the uncontrolled switch, diode is a passive switch, right? So here we cannot make the diode off state directly. Okay, so here suppose when the thyristor is in the off state, whether this switch combination will block the forward voltage. Yes, because if the thyristor is in the off state and if we are applying the forward voltage across this switch combination, then this thyristor is in the off state, means the thyristor will block the forward voltage, right? But the Okay, so the forward voltage will be blocked by this switch combination, but the reverse voltage, whether the reverse voltage will be blocked by this switch combination? Yes, whether the reverse voltage means plus here and minus here, right? Reverse voltage will be blocked by this switch combination. Suppose if I apply the reverse voltage, and even though this thyristor will be in the off state, but what will happen? The current will flow through the diode, because what will happen when the reverse voltage is applied across the switch combination? Our diode will be in the forward bias mode, so that's why the diode will be in the conduction mode. Okay, so can we say that the reverse voltage will not be blocked by this switch combination, right? So the switch is, it is a unipolar switch. Switch is unipolar. Are you getting the point? So switch is a bidirectional and unipolar, right? Bidirectional and unipolar. But in unipolar, right, the switch is blocking the forward voltage, but switch is not blocking the reverse voltage. So how will be the characteristic? Yes, switch is blocking forward voltage, but it is not blocking the reverse voltage. So here it is voltage, here it is a current, right? It is a bidirectional, means the operating points will be here and here, right? And switch is blocking the forward voltage, right? Means here will be the operating point. Switch is not blocking the reverse voltage. Be careful. Why the switch is not blocking the reverse voltage? Because when the reverse voltage is maintained, this diode will be in the on state, right? Blocking meaning is, even though if we apply the voltage, there also the current will not flow, right? Because the switch is in the off state. Okay, so here the characteristic operating points will be like this. Okay, so if you check, yes, the option B is the correct answer. Option B is the correct answer. Are you getting the point? Okay, so this is about the question number 25. Next, let us discuss question number 26. Yes, question number 26. Please read the question carefully. Yes. During the turn off process in a thyristor, the reverse recovery current of 10 ampere, is interrupted in a time interval of 4 microsecond. Right? So check the question number 26. Yes. Reverse recovery current of 10 ampere is interrupted in a time interval of 4 microseconds. Okay. Next, current is interrupted. The meaning is the current value changed from 10 ampere to the 0 ampere. Right. Interrupted means we have disconnected, or we have make its value 0. Okay. So in a 4 microsecond means in that they have given the value of di by dt. The thyristor is connected in series with an inductance of 6 millihenry with no resistance in the circuit. Okay, if the source voltage during turn off process is minus 300 volt, if the source voltage is minus 300 volt, comma, peak voltage across the thyristor when reverse current interrupted is, okay, and they have given the option. Okay, so please note the given data. It is given that di by dt is equal to 10 ampere in 4 microsecond, right? So it is 10 by 4 into 10 to the power minus 6, so it is like 2.5 into 10 to the power 6 ampere per second, right? Di by dt, so it is ampere per second. Next, L is equal to 6 millihenry. If the source voltage during turn off process is minus 300, Vs is equal to minus 300 volt, right? peak voltage across thyristor. Peak voltage across thyristor, right? That is VT peak. Okay, VT peak we need to find. Yes, and they have given the option A minus 10 kilovolt, option B minus 18.7 kilovolt, option C minus 12.7 kilovolt, and option D minus 15.3 kilovolt, right? And yes, so from the given data, can we draw the circuit? Yes, a thyristor is connected in series with inductance with a no resistance, right? So here we are having a thyristor, it is connected in series with only inductance, and we have applied a voltage of minus 300 volt. This voltage is minus 300, right? Next, this is 6 millihenry. Okay, so here current. So it is given that during the turn-off process, the reverse recovery current, yes, is interrupted. Okay, reverse recovery current is interrupted, and our task is to find the peak voltage across the thyristor. Yes, peak voltage across the thyristor means this voltage, that is the VT. VT we need to find. Okay, so from this, now can we, yes, why we have applied the reverse voltage? Because we are interested in turning off of a thyristor. Okay, so can we apply KVL? Yes, consider current here is I. Okay, because initially the thyristor was in the on state, so current flowing through the circuit, yes, it was a non-zero. Okay, so in order to initiate the turn off process, we have maintained the reverse voltage, we have applied the reverse voltage across the SCR. Okay, so it is a minus 300. Now, so can we apply KVL? Yes, KVL to loop. It is plus to minus, so it is a plus of minus 300, right? Minus VT minus 6 into 10 to the power minus 3, that is L into di by dt, right? Di by dt is equal to 0, right? So therefore from this can we find Vt? Vt is equal to minus 300 minus 6 into 10 to the power minus 3 into what is di by dt? It is 2.5 into 10 to the power 6. Okay, so from this we can write it as, yes, 2.5 into 6, so it is a 15. So it is, this one is minus 300 minus 15 into 10 to the power 3. So it is like minus 15.3 kilovolt. This is a voltage across the thyristor. Are you getting the point? Voltage across the thyristor. Yes. So what is the answer? Answer is option D. Right? Option D is the correct answer. Right? So this is the this type of questions also they have asked in the competitive exams, right? Next, please check the question number 27. Please check the question number 27, right? Question number 27. Question number 27. Yes. This question they have asked in the GATE 2014 exam. GATE 2014 exam. Yes, question number 24. Please check question number 24. Sorry, 27. 27. Yes, gate 14. Right? Gate 14. The SCR in the circuit shown has a current of 40 milliampere. So it is given I latching, that is a IL is equal to 40 milli. 40 milli means 0.04 ampere. And gate pulse of 50 microsecond, right? Consider gate pulse, that is a TP is equal to 50 into 10 to the power minus 6 seconds, right? Is applied to the SCR. The maximum value of resistor R in ohm to ensure successful firing of the SCR is, okay, and they have given the circuit. Basically this is a numerical answer type question, means this type of questions generally, yes, this type of questions there will not be negative marking, right? We have already solved this type of questions. Resistor R, this is 500 ohm, this is 200 millihenry, yes, SCR, this voltage is given 100 volt, 100 volt, right? So here we need to find the value of R, maximum value, maximum possible value. Maximum possible value of R. Yes, okay. So here we need to find the R, right? It is given that the latching current is 0.04 ampere and the TP is given, okay. Basically related with the latching current we have already discussed the numericals, but in those cases we have calculated the TP value, right? And generally they gave the value of resistor here, okay, but now they have given the TP value and now they have asked the resistor value, okay. So here corresponding to TP, okay, corresponding to TP, yes, we need to put the value of R here, such that corresponding to this time, the current flowing here, consider it is a I. Yes, I value should be equal to 0.04 ampere, right? Means at TP, if I value is 0.04 ampere, right? At that time, whatever the value of R, that value we need to write here, that value we need to find here. Are you getting the point? Okay, so initially SR is in the off state, so suppose at T is equal to 0, right? At T is equal to 0, yes, the gate pulse is applied to the SCR, right? Gate pulse is applied to the SCR, right? So SCR will turn on at T is equal to 0, right? So for T greater than 0, right? So at T is equal to 0, when SCR is in the on state, at that time what is the current here? Because before T is equal to 0, the current flowing through the inductor, yes, it was a 0, okay. So definitely at T is equal to 0, this inductor will behave as a open circuit, okay. So at T is equal to 0, inductor will act as an open circuit, so current here is 0, okay. So consider here current is I, here current is I1, here current is I2, okay, here current is I2. Next, so for T greater than 0 or at T is equal to 0, I1 is equal to 0 ampere, right? Next, for T greater than 0, yes, can we draw the circuit? SCR will be acting as a short circuit, resistor, inductor, and here unknown resistor. Okay, this is 100 volt, this is current I, this one is 500 ohm, 200 millihenry, 200 milli is 0.2 Henry, right? And this is R, we need to find. This one is I1, this one is I2. Okay, next, right? Next. So, if we check, or can we draw, can we apply KVL to the loop 1? Yes, KVL to loop 1. KVL to loop 1. KVL to loop 1. Yes, it is plus 100 minus 500 into I1 minus 0.2 into di1 by dt is equal to 0, right? So from this we can rewrite it as di1 by dt plus 500 by 0.2. So it is a 2500 into I1 is equal to 100 by 0.2. So it is a 500, right? So this is the differential equation we are having, right? So yes, next. So can we simplify it? Finding the integrating factor I of is equal to e to the power 2500 into t, right? And solution, yes, solution y into I of, so it is a I1 into e to the power 2500t is equal to integration of q 500 into e to the power 2500 into t into dt, right? So we can write it as and plus c. Okay, so this can be written as I1 into e to the power 2500 into t is equal to 500 upon 2500. So it is a 0.2 into e to the power 2500 into t plus c, considered as equation 1, right? And t is equal to 0. What is I1? At t is equal to 0, I1 is also 0, right? Because inductor was acting as an open circuit. Okay, so I1 is 0 ampere. So from 1 we can write it as 0 into e to the power 0 is equal to 0.2 into e to the power 0 plus c. So therefore c is equal to minus 0.2, right? So further, can we put this c, in 1, so it is equal to, or further simplifying we can write I1 is equal to, again I am dividing this e to the power 2500t to the right hand side. Okay, so it is equal to 0.2 minus 0.2 into e to the power minus 2500 into t. Okay, so this is the actually expression. This is the expression, right, for current I1. Expression for current I1. Okay, now yes, we need to find the value of R. Actually, we need to find the value of R. Okay, so here yes, add, we can write add t is equal to tp, add t is equal to tp. What is I? At t is equal to tp, I is equal to IL, right? I should be equal to IL, latching current, that is the current flowing through the SCR, that is anode current, is equal to 0.05 ampere, right? At t is equal to tp, I is equal to IL is equal to 0.05 ampere, right? So further, can we write it as, yes, I is equal to, yes, I1 plus I2, because here if I apply KCL, we can write I is equal to I1 plus I2, right? So this can be written as I is 0.04 at TP is equal to I1, we are having 0.2 minus 0.2 into e to the power minus 2500 into TP, right? Into TP, okay, and plus I2, okay, plus I2. Can we write I2 in terms of voltage and resistor? I2 means this branch current, right? So what is the voltage across resistor? It is 100, okay? So can we write I2 is equal to 100 by R plus 100 by R. But what is TP? TP is 50 into 10 to the power minus 6. So can we put here TP is 50 into 10 to the power minus 6? So it is 0.04 is equal to 0.2 minus 0.2 into e to the power minus 2500 into 50 into 10 to the power minus 6 plus 100 by R. Is this clear? Okay. So further we can write, yes, check this value and again shift these two terms at this side. Okay, so we can write it as e to the power minus 2500 into 50 into 10 to the power minus 6, right? So it is 0.88. Okay, so this is 0.88 into 0.2. Okay, so it is like 0.2 minus 0.1765 plus 100 by R, okay, is equal to 0.04, right? So from this we can write it as 0.2 minus answer, right? So is this one, so 0.04, so it is 0.0165, right, is equal to 100 by R. So from this can we find R? Therefore R is equal to, yes, 100 divided by 0.0165. So it is 6060.8, 6060.8 ohm, right? 6060.8 or 6061. Are you getting the point, right? Okay, so this is the question, right? They have asked in the exam gate 14. Okay, means they have not asked the straightforward question. They have given the pulse width, gate pulse width, and they have asked the possible value of R, right? Value of resistor required. Okay, so such that this I is equal to IL. Okay, next we check the question number 28. Question number 28. Yes, question number 28. Again it is a theory question. This question have been asked in the exam gate 09, right? Gate 2009. They have asked the gate 2009. Okay, question number 28. Right? And SCR is considered to be a semi-controlled device, right? SCR is considered to be semi-controlled device. Means why the SCR is known as a semi-controlled, right? Because, and they have given the 4 options. It can be turned off but not on with a gate pulse. In the option 1 they have given the SCR can be turned off but it cannot be turned on. Whether it is correct? No. SCR can be turned on by the gate pulse, right? But it cannot be turned off. Okay, so option A is wrong. Second option, it conducts only during 1/2 cycle of an alternating current wave. No, right? Next, it can be turned on but not off with a gate pulse. So please check the option C. It can be turned on by a gate pulse but it cannot be turned off by a gate pulse. Whether it, yes, is it a correct answer? Yes, this is the correct answer. Okay, and the last one, it can be turned on only during 1/2 cycle of an alternating voltage wave. This is not the correct answer. Are you getting the point? Okay, so SCR is known as the semi-controlled because yes, any switch is known as a semi-controlled because either it's turning on or turning off can be controlled by the control signal, right? So in the case of SCR, we can turn it on by using the gate signal, but whether by using the gate signal can we turn it off? No, right? So option C is the correct answer. Option C is the correct answer, right? Next, check the question number 29. Check the question number 29. Okay, yes, this question also they are asked in the exam gate 2011. Question number 29. Gate 2011, right? Yes, please check. The circuit turn off time. Yes, again it is a straightforward question, theory question related with, yes, the definition of circuit turn off time of a SCR. Please read the question. The circuit turn off time of an SCR is defined as the time taken, yes, first option, time taken by the SCR to turn off. Whether the time taken by the SCR to turn off is a circuit turn off time? No, it is a device turn off time. Be careful, okay? Second, the time required for the SCR current to become zero, whether it is a time required for the SCR to become zero, is it a correct answer? No. Third, the time for which the SCR is reverse biased by the commutation circuit. And fourth one, the time for which the SCR is reverse biased to reduce its current below the holding current. Yes, please check the option C and option D. Yes, what is the definition of circuit turn off time? Yes, it is the time measured from the instant at which current flowing through the SCR becomes zero, right? Means that time interval actually starts from, yes, starts when the current flowing through SCR becomes zero, and after that the reverse voltage is maintained. Are you getting the point? So here we are not maintaining the reverse voltage in order to, here we are not applying the reverse voltage across the SCR in order to reduce the anode current below the holding current. Be careful. Actually first the anode current is reaching the zero value, and after that we are maintaining the reverse voltage. Okay, so if you check the option C, option C is a correct answer. Option C is a correct answer for this question. Option C is a correct answer. Next, check the question number 30. Question number 30. Question number 30, right? Yes. This question they have asked in the exam GATE 2012. GATE 2012. Again, this is also a theoretical question. GATE 2012. Right? This is also a theoretical question. Please read the question carefully. The typical ratio of latching current to holding current. The typical ratio of latching current to holding current means IL by IH they have asked. In a 20 ampere thyristor is, yes, in the latching current and holding current, which one is greater? Latching current is greater, right? And holding current is slightly lesser than that of the latching current. Okay, and they have given the options 5.0, 2.0, 1.0 and 0.5. Yes. Whether both are same? No. So option C is wrong. Whether latching current is less than the holding current? No. So option D is also wrong. So please check option B. Generally the range of latching current and holding current, yes, latching current is 2 times that of the holding current, right, for the 20 ampere thyristor. So option is option B. Option is option B. Okay. So this is about the additional questions. This is about the additional questions based on the topic thyristor and diode.